Welcome to example number 2. We have a question involving a diving board. So we have a woman that is standing to the far right. She has a weight of 530 newtons, and she's about to dive off the board. The board has a length of 3.9 meters, and the weight of the board is assumed to be negligible. Over here at the fulcrum, there must be a force exerted there, and we're asked to find that force. And over here at the bolt, there's also another force there, and we'd like to find that force as well. So in our first step in solving equilibrium problems is we would identify an object, or a system, in equilibrium. And that would be the diving board. So I'm just going to draw a little rectangle here for the diving board. And we're going to draw a free body diagram for this object. We're going to make sure that we're going to show each of the forces at its point of application. So for this woman here, we're going to draw her force right acting down here. And we'll just label her force as F sub 1, which is equivalent to 530 newtons. And what other forces would you feel if you were that board? Well, this fulcrum must be exerting a force upwards on the board. I'm going to label that as F sub n for the normal force. The next is to show the force at the bolt. Remember, you have to think about what is the correct direction of each force. So I believe that force is going to be pulling downwards on here. So there's this top part of that bolt that is being pulled downwards. Now if it turns out that it wasn't pulling it downwards and it was actually pulling it up or pushing it upwards, then you'd find, even though I drew the direction downwards, your answer would become negative if you had the direction wrong. It doesn't necessarily mean that you have to redo the problem. It just means that you drew your free body diagram incorrectly. And so you'd probably need to write a sentence at the end, say, well, my force is actually in the opposite direction that I drew in my free body diagram. So I'm going to label this as the F sub B for the bolt force. In the next step, we want to choose an appropriate coordinate system. And I would say going straight up would be a good one, and to the right being positive for the x. But really there are no forces along the x-axis, and so we're just really defining a y-axis that is going straight up. Now if you had any forces that were at angles, for example, then you would have to break up those forces into their x and y components. Okay, assuming we've got all the forces drawn on the body, and we've chosen an appropriate coordinate system, we can now apply either the torque condition or the force condition. Since we're all really familiar with the force condition, let's start with that one. The sum of the forces along our y-axis should be equal to 0. That means all of the forces along our y-axis should balance out to give you 0. Now I've chosen forces that go up will be positive, and forces that go down will be negative. So summing the forces, we have the normal force going up, and we have the force for the bolt going down, that's negative, and the force of the diver going down, that's negative as well. And so if we substitute in here, we have the normal force minus the bolt force, and that is equal to F sub 1, which is 530 newtons. That's the weight of the lady. So as you can see in here, I have two unknowns, and I don't have enough information to solve for one of the variables. I need to get another equation. So maybe I should have started with the torque condition, because really I just got two unknowns, and that really couldn't solve the problem. So let's choose an appropriate axis of rotation. Now remember, your life's going to be easier if you pick an axis where one or more forces are unknown, because then the torque from that unknown force will be 0 because the position vector is 0. So I'm going to choose to, it depends on which one you solve, I guess we'll just pick the bolt. So I'm going to go over here and put a little dot right at the bolt, and I'm just going to label this, say, point A. Okay, just so that the person who's writing your paper knows what you're taking the torque about. So it's important that you label your pivot point or your axis of rotation. So we're now going to sum the torques about the axis of rotation point A. And we know that this is all in static equilibrium, so the sum of all those torques will be equal to 0. So that way, what happens is the torque about B will be equal to 0 because that position vector will be 0. So we really only have the torque from the normal force, which is producing this kind of rotation where this beam is moving upwards. So this would be a counterclockwise rotation. And then we have the woman who's standing at the far right end that is causing a clockwise rotation. Remember, clockwise rotations are considered negative torques, and counterclockwise rotations are considered as positive torques. So the sum of the torques, you could put even the torque from B, but that's 0 because, R sub B is 0. We have the torque from the normal force, which we consider to be positive because it's counterclockwise. And then we have the torque from the woman standing at the far end. We'll call that torque 1. And all of these torques will add up to 0. So to calculate the magnitude of the torque for the normal force, we will take the normal force multiplied by the position vector r sub n multiplied by the sine of the angle between the position vector r sub n and the normal force, which is a 90-degree angle. So that's sine of 90 degrees, which is just really 1. Then we have minus the magnitude of the torque from the woman, which is F sub 1, that's her force, multiplied by the position vector r sub 1, there's r sub 1, and then multiplied by the sine of the angle between the position vector and the force, and that again is also 90 degrees, and the sine of 90 degrees is 1. And all of this will balance out to give you 0. So the torque from the normal force and the torque from the woman standing in the far right end have to balance each other out. They're balanced torques. So we have the normal force multiplied by the position vector must be equal to the force or the weight of the woman multiplied by the position vector for her, R1. And now you can go ahead and substitute in. Well, you don't know the normal force, but you do know this distance. Remember, maybe it would be a good idea to label the distances. We know that the fulcrum is 1.4 meters away from the left end. So this R sub 1 is 1.4 meters. Actually, N. So that's 1.4 meters here. We have the weight of the woman, which is 530 newtons. And then we have her distance from the far end. And remember that the whole diving board is a length of 3.9 meters. So R sub n is 3.9 meters. And then you could solve for the normal force. And this gives you an answer of 1,480 newtons rounded off to 3 sig figs. Now that you know the normal force, you can either apply the force condition, substitute up here, you have 1,480 newtons minus the force of the bolt equals 530 newtons, and this will give you the force of the bolt equals to 950 newtons. Alternatively, you could apply another torque condition. So I can just show you a second way of solving for that bolt force. You could pick a pivot point right about here, point B, or you can point C. It's up to you. And we're going to do the sum of the torque, say, at point B, just to show you this torque condition applied for a second scenario. All of this balances out to be 0. Now, in this particular case, the normal force will produce no torque because the position vector at that point of axis will be 0. So there will be no torque from this normal force, but there will be a torque from the bolt force causing it to go counterclockwise, which is a positive torque, and then we have the woman producing a negative clockwise torque. So we say the sum of the torques about our point of axis of B equals 0. We have the torque of the bolt, which is positive, minus the torque of the diver at the far right end, torque 1, equals 0. Now remember, the magnitude of this torque is not the same that you got here because we were taking a torque about this axis point right here, and the length was a total of 3.9. Now R1 will change. Let me show you what I mean. So the torque, the magnitude of the torque from the bolt will be equal to the magnitude of the torque produced by the woman. The magnitude of the torque from the bolt will be F sub B, which we now know, or we're trying to find actually, multiplied by the position vector r sub b, and this will be equal to the force of 1 times r sub 1. I'll just make this as r sub 1 prime because it's not the same as it was before. So the bolt force multiplied by r sub b. Now r sub b would be this distance right in here, which was 1.4 meters. And then this on the right side is her weight, which is 530 newtons. Then multiplied by this distance in here. And this distance was, remember the whole length is 3.9 meters. but we've already got 1.4 here. So we're going to subtract 1.4 meters from that. And we're going to get 2.5 meters. So R1, so R sub 1 primed is 2.5 meters. And now substituting into here, we will get a bolt force. If you multiply these two numbers divided by 1.4, you're going to get also 950 newtons as well. Lots of ways to solve the problem. All right, sometimes you have to sometimes go through all the different conditions, force conditions and torque conditions, until you find an appropriate equation or set of equations to solve the problem. By the way, had this board had a weight that was not negligible, where would you draw that force? You would draw it right about here, which is at what we call the center of gravity. Okay? The center of gravity can be easily determined from objects like of uniform mass density. If it's uniform mass density, then it's just really take that total length and divide by 2, and that's where it is. The center of gravity, which you'll see me label as CG, of a uniform object such as a meter stick, is at the midpoint, its geometric center. The center of gravity is essentially that balance point. If you were to put your finger at that single point, you could support the whole object, because you'd be applying a normal force straight up above or below this little red point, which is the center of gravity, and you're going to assume that all of the weight of the meter stick were concentrated at that one single point. So it's assuming all the weight of the meter stick were concentrated at that point. That's why you can balance a meter stick with one single upward force directed at that point. Okay, and that's it for example number 2.